Hey everybody, this is the Formulas and Naming Review video in which I'm going to go over some of the gist of how we write formulas and name compounds based on the formula, converting between back and forth, practice some problems, just in preparation for the quiz about this topic, okay? And so let's start with the basics of reading formulas. And so formulas have a purpose. What do they tell us? They tell us the elemental composition of the compound. So they tell us specifically which elements are part of the compound and how many. So it's all about the element composition of a compound. Okay? So I'm just scribbling here. Okay. And what do the subscripts mean? So if I were to give you an example of a formula, I'm just going to make one up. I mean, this is accurate, yes, but what do these subscripts mean? They tell us specifically, if you look over here, these subscripts, these small numbers there, they tell you the amount of atoms of that specific element. So in this example case, we have 2 of NAs and 4 of the oxygens here. 2 sodiums, 4 oxygens. They tell you here number of atoms of the element. Okay. And what does the coefficient mean? So let's say you have a coefficient, and this coefficient is placed right in front, right there. So that 2 does not apply only for the Na, it applies to the entire compound. So think of it as a 2 outside of the parentheses. So that means we have 2 of the full compounds. So how many atoms you see within one single Na2SO4, you multiply it by 2 because it's saying that 2 there, it's saying that we have 2 full compounds right there. So number of the full compounds. Okay. And so on this slide, I'm going to go into the gist of naming customs and formula writing. So there are 2 different compounds we look at. Binary compounds, which is essentially ionic compounds, and then there are covalent compounds. So depending on the type of compound you're looking at, there are 2 different methods of naming and formula writing. And so most of the focus of this quiz will be on binary ionic compounds, in which we use the criss-cross method. Very rarely you'll encounter some covalent compound examples where it's all based on the prefixes. So here. So let's start with the binary ionic compound. And to tell whether or not you're looking at a binary compound, you have to look at the type of elements. So commonly ionic compounds, as we talked before, is metal plus a nonmetal. Okay? Now if you see here, polyatomic ions, what are those? So poly meaning many, atomic meaning atoms. So they are ions composed of many atoms, okay? So those you're going to have to look for in the reference table. I'll elaborate more on that later, okay? So if you see a polyatomic ion combined with either metal, nonmetal, or itself with another type of it, then you're likely looking at a binary compound. And I'll elaborate on the criss-cross method with some examples later. Whereas covalence is just nonmetals together, and they have specific prefixes to tell you the number of atoms for that compound. Okay. So here are some general rules that apply to all examples here. So which types of elements keep their names and which have the IDE ending here? Okay. So to elaborate on that, let's start with metals. And then there are nonmetals. Oops. And then there are polyatomic ions. I'm just writing really fast here. Okay, so metals, they keep their names. So you always see them come first. They're going to keep their names within the formula. Nonmetals have the IDE ending, and then polyatomic items, they keep their names also. Okay. Now, if you see a strange name that doesn't sound like an individual element, so for example, nitrate, chromate, sulfate, so then it's likely a polyatomic ion. And where do you find those? You're going to find those on table E. of the reference table, okay? Now, talking about binary compounds, you're going to use the criss-cross method to determine the formulas and the names. So criss-cross methods meaning you need to look at their oxidation states. So that means looking at the reference table, periodic table, and looking up at the top right corner for their charges. For example, oxygen. Okay, so this is number 8. So up here in this top right corner, that's the oxidation state. So every time you see oxygen, it's going to have a -2 charge, a -2 ion, and such. Okay, and then you crisscross those subscripts down as subscripts. Okay, those oxidation states as subscripts. So as an example, let's look at barium oxide. Okay. Oh, well, that's a cheap shortcut. Okay, never mind. Let's go back and I'll give you guys a different example. All right, let's try potassium oxide. Okay, so potassium, we're going to follow this method of giving the formula. So potassium here has the element symbol of K, and its oxidation state in the reference table is +1. Oxygen is going to have -2, or 2 minus. The method here, the crisscross, you take their oxidation states and you crisscross them down as subscripts, and you just remove the signs. So it's going to look like this. Oh, let me use a different color. So that K is going to get a 2, and this oxygen is going to get a 1. Now, if you see 1s down there, you don't need to write the 1. You can just remove it like that. So it's just K2O. So that is how you write the formula. Now, going the opposite way, you're going to do the reverse crisscross. In most cases, you don't need to do that. But the cases that you do need to do the reverse crisscross is when you have to use Roman numerals. Okay? So when you have metals, for example, manganese, iron. So as an example, I would probably say iron oxide. So let's say you have Fe2O3 as an example. What if you want to get that as a name? So this is where the reverse crisscross method is useful for. When you have elements like iron, iron has 2 oxidation states, +2 and +3. We don't know which one it's using, so that's why we do the reverse crisscross. -2 here, this one's +3, okay? So that means it's using the +3 state, and so Roman numerals there are there just to tell us which cation it's using, which positive oxidation states it's using, okay? And so when we write this out, it's not just going to be iron oxide, it's going to be iron 3 oxide, okay? So a lot of cases like potassium oxide, you don't need the Roman numeral because potassium only has 1 oxidation state, but iron here has multiple. A lot of transition metals follow in that category. So because it has multiple oxidation states, we need Roman numerals to indicate which one we're using, okay? Now, covalence. This is on the easier side because all you do is have prefixes. They're already set. So some of these prefixes are simple to remember. If you are in geometry, these might be familiar. Okay. Penta is 5, hexa is 6, hepta is 7, octa equals 8, and then I believe is 9, and this is 10, if I recall correctly. Okay, I could be wrong for the later half, but I'm just going off the top of my head. All right, so that's what the prefixes stand for. and they tell you the number of atoms for the element specified. So the leading atom, so that means the first one listed there, they sometimes don't need a prefix if they're alone. And what do I mean by that? Okay, so let's see. Let's look at CO2. So carbon, being the leading atom, only has one of itself. So it doesn't need the prefix. You're not going to say monocarbon. But there are two oxygens. So you're going to look at the prefixes. It's going to be carbon dioxide. Okay? So it's not going to be a monocarbon dioxide. It's just carbon dioxide. If, however, you have multiple carbons, that's when you're going to attach the prefix. So the leading atom, like carbon in this example, doesn't need a prefix because it's by itself. It's only singular carbon here. And so the main point of this is to really, the way to best study this is to practice, practice, practice. This is the kind of unit where you just need to practice, practice, practice. Writing formulas and writing names, okay? So here's a slide full of formula writing practice, okay? So sodium oxide, we're going to use the binary methods of criss-cross, okay? So, because we're looking at an ionic compound. So sodium, +1. Oxygen, -2. Criss-cross them down to the bottom, Na2O. That's it. Potassium sulfide, okay? Keyword there. Not to confuse with sulfate. So potassium is K, that's a +1. Sulfide is -2. Criss-cross them down, K2S. Okay. Barium phosphide. Again, look out for the "ide" ending, so it's just the normal element. So barium is +2. Phosphorus is normally -3. Okay, it has a lot of oxidation states. Some elements are like that, but for the most part, if it's bonded with a metal in a binary compound, it's likely going to be a negative ion, and -3 is a common example. So criss-cross them down. Okay. You're going to see barium 3, phosphorus 2. Barium phosphide. Okay. Calcium nitrate. So this ending here indicates we're looking at a polyatomic ion. It's not nitride for nitrogen. It's nitrate, which means it's polyatomic. So calcium is +2. Nitrate is NO3. And that we need to look up on the reference table. And you'll see on the reference table, it has a -1 oxidation state. So again, you're crisscrossing down. Now you're going to see something different here. So Ca doesn't get a subscript, but I'm going to put these parentheses. Why? Because we have a 2 subscript. This 2 goes for the entire NO3. Okay? So that 3, that NO3, some people think 3 is for the entire thing. No, it's just for the oxygen, but the 2 here is for the entire NO3. All right? So you only need parentheses when you have multiple of the polyatomic ions. Okay? Now, iron 2 chromate. So here we have a Roman numeral. So that 2, Roman numeral 2, is for the +2. That means iron is Fe. That Roman numeral 2 means it's +2. Chromate, reference table, polyatomic ion, is CrO4. Okay? And that has a -2 charge. Criss-cross them down. Okay? So Fe2, CrO4, 2. Now, because we have even subscripts here, we could simplify it further. So only with binaries that you could simplify these down further to make it Fe, CrO4, and that's it. Now, chromium 6 chloride. Cr +6, Cl -1. So chromium chloride, it's a 6 there. All right, and that's it. And then finally, we're going to go into naming. Now manganese, Mn, look on the reference table, manganese has multiple oxidation states. Okay. So let's see. Manganese, that's when we're going to do the reverse crisscross. This is going to be a +2. This is a -1. So to indicate which one we're using, Roman numerals, we figure out it's using +2. So we got to write Roman numeral 2 there. And then chloride. B, sodium only has one oxidation state, so we don't need to do any crisscrossing. So it's just sodium fluoride. That's in toothpaste. C, potassium sulfide. So all you're doing is just looking up these symbols and their names, in case you didn't know their names by now, which you should after quizzing it multiple times. All right, next. Now we have a covalent. All right, we're not dealing with metals here. Okay, so carbon dioxide. Carbon, because it's the leading element. It doesn't need a prefix, doesn't need to say monocarbon. And then 2 oxygens, the prefix is di, carbon dioxide. Now E is an example where the leading atom has multiple of itself. So now we need a prefix with nitrogen. Di-nitrogen for 2, and because we have 5 oxygens, it's going to be pentoxide. Pentoxide, pentoxide, same spiel. Okay, penta meaning for 5. Now this. Carbon, again, leading atom by itself, and then oxygen, there's only 1. So here, even if it's by itself, you still need the prefix. So carbon monoxide. All right, and voila. We had some practice. I hope this was useful for you guys and helpful. And don't forget to ask questions out of us teachers in case you need some further clarification. Good luck on the quiz. Hope this was helpful. Take care, guys.